Okay, so we're back September 17th, 522, and this is part two. So before the break, we were reviewing more concepts to regression. And as I mentioned, I will get to the nearest neighbors a little bit. That's a non-parametric approach. And we want to kind of go into that a little bit as we push forward, but not just yet. So have a read of that stuff, and we will recap that as we go forward. Now we get into this idea of classification in statistics and learning models. And when we talk about classification, we're usually talking about classifying into one or two possibilities. So as we said before the break, we have 0, 1. This is now binary. So we may have our predictors here, but we have to classify into one category or another. Now, just as a big picture item, this doesn't look that much different than in regression, because in regression, really, in a strong sense, we are actually classifying as well, right? We're trying to predict values on the response. It's just that there's a much wider range of values. So you can think of it that way too, that this idea of classification, we've kind of been doing something similar in linear regression. Only in linear regression, there's many more categories. Now, beyond that, there's going to be some differences in some of the methodologies we use. So the first one we're going to look at is we're going to look at logistic regression, which makes some serious alterations to the classical regression idea. Qualitative classification, these are often called classifiers. Okay, this is kind of like the hip language for logistic regression and discriminant analysis these days. It's called classifiers, or you can just call it logistic and discriminant analysis. It's fine too. The k nearest neighbors is this idea we want to talk about pretty soon, because that's going to be a non-parametric approach. So first, let's get into the logistic regression. The k nearest neighbors is going to build on the idea of k nearest neighbors from the previous chapter. So have a read of that. When we get to k nearest neighbors here, this will make more sense. And again, I'll review those things once we get to the k nearest neighbors. So overview of classification, you can have a read of this. You have somebody who arrives at the emergency room with a set of symptoms. Well, they could be attributed to one of three medical conditions. Which of the three do they have? Notice that when you classify based on variables, you may be losing information, right? So it's kind of like when you produce a factor out of a continuous variable in regression on the independent variable side. It's not always a good idea to do that. So, don't be in too big of a hurry to kind of want to make that response variable binary or multi-categorical. If it's continuous and it's got a pretty good distribution, you're probably safe with regression, right? A lot of the techniques that we look at, we still come back to the idea that regression is often a really good thing to do. Okay? So you don't want to be like producing a whole bunch of categories if you can just deem that to be more or less continuous. Could be useful for like banking service, for DNA sequences and stuff like that, where you have to predict whether the transaction is fraudulent or not. So that's kind of nice. And that's kind of the thing where when your credit card, clicks off and they don't let you use it anymore, well, maybe you've been classified into the high risk group, or maybe a suspected fraud going on. So they're using these classification algorithms all the time. Here we have different categories. So we have one category here and another category here. The individuals who defaulted on the credit card payments are shown in orange, and those who did not default in blue. So maybe we want to predict those categories. Now you look at that and you see the overlap. So you see the problem. Everything would be nice and neat if these categories were completely separate, but you're going to have some overlap. And that's what these models try to do, is they try to, how are we going to parse out that overlap and develop a model that predicts with some accuracy, that classifies with some accuracy. And again, when you're looking in the machine learning literature, these are regarded as classification algorithms. So when you hear someone talk about, I'm going to do like a machine learning model and classify, they're often using things like logistic regression. So why not use linear regression? Okay, well, linear regression assumes continuity. So if there's a response variable, linear regression assumes this to be continuous. That's really, really important. But if you have data like this, that's categorical, nominal in nature, then that linear regression model doesn't apply. So if you entered your data wrong, okay, if you entered it as 1, 2, 3, and you assumed it was continuous, right? You put this in as continuous data when really it's nominal, categorical in nature. What is the regression program going to do? The regression program is going to go, I see this is 0 and this is 1, this is 3. This is based on a continuum, and it's going to model that as a continuous variable. So you definitely don't want to be doing that. As we're going to see, for the case of a binary response, the situation isn't as bad. Even if you made a mistake and you did a linear regression on a binary response, it ends up not being too bad of an error. But definitely once you get into 3 categories, and if you do higher, you definitely don't want to be doing that. Now, what happens as the number of categories increases? Well, maybe you can put some continuity to it if it makes sense, right? So, how much money do you have? Would you have a little bit more, medium, more? Maybe eventually you start to say, instead of having categories here, maybe I'll consider this to be continuous and go from a range of 1 to 5. So again, fuzzy distinctions depends on how you're operationalizing the variable. So realize, what you may have in your data may be transformable to a different variable if the situation calls for it. So it's not always clear what you want to do, but keep those things in mind. They make a comment here. They say, unfortunately, there's no natural way to convert a qualitative response, the categorical values, with more than 2 levels into a quantitative response that's ready for linear regression. Well, I kind of just disagreed with that, right? Because in research, researchers do that all the time. And they say, well, we're going to transform it into a different variable. So I don't fully agree with that, and just be aware that, sometimes you may want to do that. So let's consider the case of the binary variable. We have the dummy variable with this binary 2 categories, 0 if stroke, 1 if drug overdose. You may want to categorize into those. What's the problem with using linear regression? Okay, so the problem with using linear regression is that some of our estimates, okay, will be outside of the 0-1 interval. So when you're actually trying to predict, if you use just classical linear regression, we're going to see that you can actually get probabilities that are out of bounds. So here's the probability of drug overdose given X, but if you use a classical linear regression, these probabilities may be out of bounds for this. They're out of the 0-1 interval. So we know probability is between 0 and 1, but if you use classical regression, you may get something outside of that. But interestingly here, the actual linear regression to predict a binary response will be the same as the linear discriminant that we're going to look at later. So there are situations where the models actually produce almost the same information, but we should still model it correctly to avoid, especially in this case, those bound problems when you estimate probabilities and such. So you really shouldn't be doing regressions on binary variables. You should be doing logistic regression or discriminant analysis. So what does logistic regression do? Well, logistic regression models the probability, okay, that Y belongs to a particular category. So it's looking at the probability. Now, how it gets to the probability, we're going to see is a little bit complicated. So here's a situation where we're trying to classify and we're using a linear model. Well, the linear model could actually produce this negative probability of defaulting, whether you'll default on the credit card loan or not. Whereas here, it's not negative. So here's the immediate benefit of using the correct procedure, logistic regression, is that you're not going to get out of bounds probabilities. So you definitely want to use the logistic in cases where you have the binary. logistic or discriminant analysis, but our first consideration here is logistic. So you want to model the probability that you default yes, given your balance. This is your predictor, and there's your response. Notice that's a conditional probability. So we can predict default yes for any individual for which the probability of the balance is greater than 0.5. Sometimes you can alter that probability too to change the sensitivity of your model. You may not want to have it at greater than 0.5. You may want to have it at greater than 0.7 or greater 0.8. That has to do with those type 1, type 2 error rates on which error of classification is most important. But typically, it's going to be set at 0.5 by default. So how does the logistic regression model work? Well, some of you have seen this before. And if you're in my 521 class, some of the final exam actually featured a little bit on logistic regression as a kind of like a bit of a warm-up. So what we want to do is we want to take the probability and we want to convert it into a linear model. Okay, this is the idea. Now, let's look at how this works. We're going to use this logistic function. The logistic function is up here, and it's kind of like a sigmoid function over here. So it does this, and then it rises for probability values, but notice they stay within the bounds of 0 and 1. So the probability of x is equal to the exponentiated logit. Okay, so this thing up here, this whole function up here is going to be called the logit. We're going to see how the logit arises in a second. But this is what we're going to be dealing with. So we're going to be modeling the probability. How we're going to model it, we're going to use maximum likelihood for estimation. So that's how we're going to estimate our parameters. In regression, we used ordinary least squares. In this case, we're going to use maximum likelihood. It's going to have that S-shaped that we looked at just above. So when we change this around a little bit, we're going to get what's called the odds. Okay, really important. Here's the odds. The probability for a given category relative to the probability of not being in that category. So for mutually exclusive events, we have probability of surviving versus probability of not surviving. Okay. This is equal to what I just said, the exponentiated logit. So what we need to see is how are we actually getting this idea up here? Okay. And why are we exponentiating it? Well, it's the odds on this side, okay, equal to the exponentiated logit, and the odds take on any value between 0 and infinity. Values of odds close to 0 and infinity indicate very low and very high probabilities of default, respectively. So you can look at that example in terms of where those odds are going to be. If 1 in 5 people with an odds of 1/4 will default, since probability equals 0.2 implies an odds of 1/4. So you look at those, you say, well, you have 0.2 over 1 minus 0.2, and there are your odds. Okay. Now, the odds idea, be careful not to use odds analogous to probabilities, because they're not. The probabilities are used in the odds, but they're not the same thing. So like careful on assignments, because we sometimes talk about that, right? We just say, hey, boy, the odds are 0.7, right? Well, the odds are not 0.7. The probability may be 0.7, but the odds are a little bit different. So what's wrong with the odds? Well, there's nothing wrong with the odds. The odds are used at, horse racing, and they're used on betting strategies and stuff like that. And you hear about odds being reported. However, the odds, there's a problem, is that the odds do not produce a naturally linear model. Okay, so what we're going to do is we're going to take this odds and we are going to convert it by taking the logarithm of the odds. So we're taking the logarithm of the odds, and when we produce the logarithm of the odds, we get something here that looks a lot like our original regression equation, right? When you take the log of the odds, we get something that's linear in X. This is the key to logistic regression. This is what logistic regression does, is it transforms this rough looking variable, right? And it's rough looking because it's like it's like, think of it as almost like not being very smooth. If you want to think of it that probability of X over 1 minus probability of X, wow, that's kind of like rough and weird. Let's convert it by taking the logarithm. And this gives us a linear model in X, but we're no longer modeling the natural units of X. These are not the natural units of X. We are now modeling what's called the logit. So all of this is now producing a coefficient on this new scale, which is called the logit, the log of the odds. So when you input a value for X, you're outputting the log of the odds. You're not outputting what you would get in the classical regression setting. So when we do y is equal to a plus bx, up to now, when we've inputted for X, we got the predicted value given this input. Now it's a little bit different because this new value here, right, our predicted value, is now in terms of this thing called the logit. It's not in terms of the original units. So it's not going to make sense to interpret y on its own, right? Because otherwise we're interpreting something in the logit. So we're going to have to see how we can convert that. So how do we actually interpret this? For a logistic regression model, increasing X by 1 unit. So you increase X over here by 1 unit has the effect of changing the log odds by B1. That's the difference. Again, so it's not the same thing as this idea. It changes the log odds. Now, it multiplies the odds by e to the B1 because we're exponentiating the coefficient. We're exponentiating the coefficient to get that multiplication by the odds. Now, important here in terms of interpretation is be very careful that a 1 unit change in the log odds, okay, a 1 unit change in the log odds, it's not increasing the odds in the traditional sense of regression. It's not saying for a 1 unit increase in X, we increase the log odds by B1. That's not a very good interpretation. You see that interpretation sometimes and you just got, it's a little bit crude, but it's not the best interpretation. The much better interpretation is that multiplies the odds by e to the B1. Okay. So we see that odds are multiplicative in this case. It's not the same thing as the classical regression situation. Now you can see from the odds up here, if the probability is 0.5 for the event that you're interested in modeling, then 1 minus 0.5 is 0.52, so you're going to have 1. Even odds, 1 to 1. As this probability gets higher, well, you're subtracting out a lower term here, so the odds increase in favor of the event that you're modeling. So here's what they say here, right? Because the relationship between the probability of X and X is not a straight line, right? It's not a straight line. B1, the coefficient, does not correspond to the change in probability associated with a 1 unit increase in X. It's not linear in that way. So we need to remember that. We'll see that again in a second. Let's estimate the coefficients. Well, I think I mentioned we estimate them by maximum likelihood. Maximum likelihood may be familiar to most of you. We've talked about that in previous courses. We're maximizing the value of the parameter that represents the data, right? So which parameter is the best one to choose? Well, whichever one for which the data is the most probable. So when you think about maximum likelihood, you're really dealing with a situation where you're saying what's probability of the sample given the parameter here. Okay. Which value of the parameter makes the data, the sample, most likely? So you could have a choice of parameters. You could have this parameter, you could have this parameter, you could have this parameter, you could have this one, and the maximum likelihood here, the one that you're going to use, is whatever one that maximizes the probability of that sample or data. That's basically how maximum likelihood works. There's the likelihood function. It's often used in nonlinear models, whereas the least squares is used in the linear case for regression. Maximum likelihood often finds its place in nonlinear models, and we'll be seeing it more throughout the book. Okay, so let's look at how to interpret this. So we've run our logistic regression, and we have balance here. So we're trying to predict, classify the probability of default. Well, there's our balance over here, our predictor, and we're trying to predict the probability of default. Now, default, remember, is a binary variable, yet we're trying to predict the probability of default. So right away, that should kind of, you think about it, say, we're predicting the probability of default, even though default is 0, 1, right? Default is 0, 1. So again, what's going on is we're converting the 0, 1 to a probability scale. That's how we're able to get the probability of default. Again, how do we do that? Well, we take the odds. We take the log of the odds. So you think of that, that odds is working on that binary category. But when you take that log of the odds, you're linearizing that information into a linear model. And this here is now in units of the logit. Okay, it's now in units of the logit. So how can we interpret this coefficient for balance? Well, we can say for a 1 unit increase in balance, okay, the corresponding change in the logit is 0.0055, right? That's different than in the traditional regression, where we would say for a 1 unit increase in balance, we expect y to change by this. Now, we are in units of the logit, the transformed variable. So our first step is having this as the logit coefficient. On the logit coefficient, we can compute a z-statistic, very similar to the t-statistics we compute in regression, and we get our p-value. So we know that that is statistically significant. Let's make predictions using our logistic regression. So once we've estimated our parameters, and there's our estimates there, right? There's our intercept, and there's our parameter estimate for the input variable. Well, what I'm going to compute is the probability. So I'm going to take exponentiated logit. That's what that's doing. There's a logit up there. We're exponentiating the logit. Here we're exponentiating the logit. So this is for one category, and this is for another category up here. Okay. So when you think about this, what you're doing is you're getting the probability of the value you're modeling, okay, of the value you're modeling. Since we're modeling default here, then we're computing this over this is equal to the probability of default. So the predicted probability of default for an individual with a balance of 2,000 is much higher and equals 0.58. This is for a low value, and this is for a much higher value. But there's your probability of default. Now this is for 1,000 over here. That's the input variable, x, and there's x over there. So you've input x, you exponentiated the logit, you've exponentiated the logit, and you're getting the predicted probability of the default value. Okay. But again, you see how this is working, right? You're translating that binary information into a probability so that you can use it in a regression-like context that we've been doing. Because it looks very similar, but we had to take that step of computing this logit idea, which is what we're seeing up here. So there we go, predicted probability. We can also use qualitative predictors in the regression model as via the dummy approach. So you can do that as well via the dummy approach we looked at. We can look at student yes versus student no using our previous example. So this gives you the probability of default for a student in the yes group because they're coded 1, right? That's yes, and coded 0 for no. And that makes the logistic regression model pretty flexible too, because then you can say, okay, what's the probability of default if you're coded 1 versus 0? If you're coded 1, there's your probability of default. If you're coded 0, there's your probability of default. We can also do multiple logistic regression. Okay, we have several predictors, but the idea is the same. Okay, take the log of the odds and get your linear equation. We can rewrite it like this as we did just up above, and we can get all of our coefficients in here. So remember, the response variable is binary, and these are our predictors. Okay, so we have balance, income, and then student, yes versus no. One point here, the negative coefficient for student, okay, is that for a fixed value of balance and income. What does that mean? That's holding balance and income constant. So see, those rules still apply. This is all model specific information, right? So, when we're estimating these things here, it's holding all the others constant. So, the coefficient here for balance, for a 1 unit increase in balance, how much does the logit change? Well, the logit expectedly changes by this much information because that's the coefficient for balance. So on for income and so on for student, right? For the student one, it's coded yes here. So this is the change from 0 to 1. Okay? From 0 to 1, holding this information constant. Okay. Okay, so one note here, they talk about confounding a little bit. Just a note to say that, remember, it's the point that I just talked about, that remember that your data is interpreted in the context of other predictors. So your coefficients are always relative to the model, and they're calling this confounding. A little bit more than confounding, right? For us, it's like, is your model correctly specified? The dangers and subtleties associated with forming regressions involving only a single predictor when other predictors may also be relevant. That's huge, right? That's huge. Like, that's hardly a footnote. It's a footnote in this book, but you can develop that into a whole chapter and talk about how important that is when you're estimating a model. If your model is not specified properly, then all of these estimates are going to be off. And I hope that's appreciated, that if there's more predictors out there that should be included, but are not, then all of these estimates are wrong. So we know that all models are wrong because you're never going to have the perfect specification, but you want to make sure that your model is specified as well as it can be. Otherwise, you're literally interpreting a coefficient for X1 that's going to change as soon as you put in X4 and X5. And that's why on your committees and things like that, people say, well, what about this variable? What about this variable? So you have to somehow include the most relevant variables. Otherwise, it's misspecified. So what they're talking about here in terms of confounding, also think of the misspecification of the model. More stuff here. You can have regression, logistic regression for greater than 2 response classes. That can sometimes be done. Oftentimes these things work their way into binary categories. So you don't want to be doing like 4 or 5 categories usually. Usually try to make it binary. And if not, you could also do this in terms of a discriminant analysis, which discriminant analysis can be used for multiple class classification. Okay. And that's what we're going to be starting to talk about next week when we continue this. Now, the lead up to this, to discriminant analysis, we need to first talk about another statistical model, one that is not featured in the book, that I am going to post some readings on, a chapter from a different book. Yeah, where we're introducing another book into it. You'll like this book in terms of a reference manual as well. And that is talking about the MANOVA procedure. Okay, so let's talk a little bit about what MANOVA is up here, because as we're going to see, MANOVA and linear discriminant analysis can be considered opposites of one another. Now we're going to see how that comes about. Now I want to make one point, is the logistic regression model that we just looked at, that has a binary response, right? Linear discriminant analysis often has a binary response. But that does not mean logistic regression is the opposite of MANOVA. Okay, that would be a mistake to conclude that simply due to the nature of the response variable. Okay. What we're looking at here in terms of this relation between MANOVA and discrim is special to MANOVA and this particular classification model. It's not classification models with 2 categories are all similar to MANOVA. Just want to make that clear. So let's think about an idea where we'd want to do a MANOVA and what MANOVA is. And then you can look in the readings I'm going to supply for that. And next week we'll survey the MANOVA model in some detail before considering the linear discriminant analysis model. So what is MANOVA? Well, you can see that MANOVA has ANOVA in it. And in the classic ANOVA model, we have Y, and we have, say, like this. Okay, you might have a factorial with x2, x3, but let's just say it's a one-way for now. So you have the response variable, and then you have the categorical independent variable. Now, what the multivariate analysis of variance does, and this is a really important point to understand how this all works, is instead of considering only a single response variable, so instead of considering just y1, it considers y2, maybe y3, etc. So it's going to consider a combination of response variables. Okay, a combination of response variables. This one here is going to stay the same for now. It's still categorical. So the question is, why would you want to include more than a single response variable into the same analysis? Well, we immediately see, first of all, on the technical level, that this is different than ANOVA. Why? Because this combination is going to be called a linear com. Okay, a linear combination, which we know what a linear combination is. I'm going to put the linear combination down here. Y equals AX1 plus AX2 plus AX3. This will be 1, this will be 2, this will be 3. That's a linear combination, and that's right out of Fox. So the linear combination of response variables, we're saying, is a function of this categorical variable, this factor. So now think about this. Why would I want to choose that linear combination? Well, I'm going to choose a classical example here that maybe this is verbal IQ, this is analytical IQ, and this is, say, quantitative, I'm saying IQ, abilities, verbal ability, analytical, and quantitative ability. When you look at these things, you might hypothesize that these almost form what's known as a variate, right? Some kind of variate and not a variable. It's a variate because it's a combination of other variables. And you might wish, for the sake of example, to consider this to be something like IQ, right? So these observed variables you may wish to consider, in a sense, to be some kind of a latent dimension. Okay? Latent dimension, even though I'm only using the word dimension here kind of loosely because we're going to do dimension reduction when we do the discriminant analysis and when we do principal components, etc. You usually wouldn't consider this to be a dimension here. You just consider it to be a combination of variables and some kind of a variate. Okay. So you can, if you want, you can say, well, we kind of got a dimension here, but you're not really analyzing it for dimensionality. You're analyzing because you want to combine the variables together. So there's a slight difference between those two things because I don't want us to confuse MANOVA with like principal components analysis and factor analysis, because they're not the same. Here, we're not actually seeking dimensionality. We're hypothesizing that these things go together. So if you want, you can say, well, this is kind of like a hypothesized dimension, but it's not digging into the procedure and trying to uncover dimensionality. Principal components analysis and factor analysis will do that. We'll try to see where is their dimensionality. Here, you're including them. Okay, so there's a difference between the two, and I'll have more to say on that dimensionality word as we move forward. So we have a rationale for why we would want to consider these variables together, because we think there's maybe some latent variate, some structure to combining these things. Here's what the question is then. If it's a linear combination, which mathematically that's all it is, it's a linear combination, how are we going to choose these? And what are these? Well, these are weights and these are scalars, right? These are scalars. So what I'm about to mention is a really, really important unifying point. The choice of these scalars, okay, the choice of these scalars should depend on some function we wish to maximize in this particular setup. Okay, the choice of these scalars should depend on some function we wish to maximize in our data, in our relation between the response and the independent variable. Now that may sound analogous to the idea of linear least squares, where the scalars, right, a plus b x, these scalars were chosen to what? Minimize the sum of squared errors, right? Minimize the sum of squared errors. So in other words, these scalars here were chosen, let's just say, in a very intelligent way. Now by intelligent, I'm just meaning there was a rhyme and rationale for why they were chosen that way. Those were the least square solutions, and they guaranteed this condition was going to be satisfied. Okay. Now I hope that makes sense. So what we want to do here is we want to choose these scalars in such a way that some function of the data is maximized here. So what would we like to maximize? Well, I'm just going to reduce this down to a two-group problem. So there's just two groups on our independent variable. What would you like to maximize in the selection of these scalars? So in other words, if I selected this to be 1, this to be 2, this to be 3, the question you could ask is, what is that satisfying? Right? What is that satisfying? What function is that satisfying? And that selection, which we can call it like a naive selection of 1, 2, 3, is not satisfying anything because it's just ridiculously chosen. I just chose them arbitrarily. It's like choosing the intercept 5 and this is equal to 10. It's not minimizing anything over here in the OLS sense, in the least square sense. So pause for a second and think about what function should be maximized here. Well, I want to see if there are mean differences between these two categories on this linear composite. But I'm not really told what I'm maximizing. In order to know what I'm maximizing, I need to think about it in terms of a discriminant analysis. So I'm going to take this equation. The reason why I'm talking a little bit slower here is because these are really vital points here. All the stuff I'm doing on this page is really kind of like overlapping things that we're getting into. I'm going to take this information here and I'm going to flip it. Okay, I'm going to flip it around. So I'm going to take X and I'm going to put the two categories here. I'm going to take Y1, Y2, Y3 over here. So I flip the roles of the independent and the dependent variables over here. And this question of maximization will now make more sense given what we've talked about with logistic regression. So if I combine these variables in this way of combining them by linear combination, what should you want to maximize when predicting or classifying on X? What would you want to maximize? You want to maximize the separation between groups, right? You want to maximize the separation or distance between groups. Okay. Now, what does that mean exactly? What that means is that if you choose these scalars in a very smart way, then that linear combination that you compute is going to generate the most difference between these two categories. It's going to classify the best it can. That's the logic of discriminant analysis, using a linear composite to maximally separate groups. That's what it's doing. So if I have like two overlapping groups, I'm going to try to find a new function. There's my new function that provides the best discrimination between those groups. That's what discriminant analysis is doing. Now, the book here, in this book that we're looking at, doesn't talk about that in terms of the MANOVA. It doesn't talk about MANOVA at all. But in the book that I'm going to post online, because I'd like you to read a few chapters from there, I'll be covering them next week, kind of a survey of them, because we want to talk about the MANOVA. This book doesn't, but we want to talk about the MANOVA. They're going to emphasize that. And it's kind of unfortunate that they don't even mention MANOVA in here, but it's vital that we understand this relationship. Not only because some of you will eventually do a MANOVA, but also because this relationship is really, really a powerful relationship to realize between the two. So I'm choosing scalars for my linear combination in order to, when I flip it around, maximize separation between the groups. That's how these scalars are being chosen. Now, if I return back to the MANOVA problem here, MANOVA in its own right is interesting. I don't need to talk about it in this sense. I can still talk about it in this sense and say that I'm looking for group differences, one group versus the other, on this linear composite. If I found those group differences, what could I conclude? Right? I can conclude that with a combination of verbal, analytical, and quantitative, there's mean differences between two groups, because I have two groups up here. So I can think of it like that. Now, these are now becoming vectors. So I'm looking for not mean differences, I'm looking for mean vector differences, because I have vectors of variables here. I have one vector in one group and another vector in another group. So that's why we need that vector notation here, that vector idea. Okay, so what I'm going to do is I'm going to post some of those MANOVA notes online. There's like about 3 chapters in there. Definitely do not have to read or cover that all, but I'll explain in an email a little bit how to approach that reading and what I'm going to cover next week. And then if you need to do a MANOVA you can see that in that book, there's more details you can get into. We'll talk about all that next week. But it's crucial that we survey the MANOVA like this and in that other book so that we can return to linear discriminant analysis and see how those two things relate. Okay. Okay, so what have we covered today? Well, we finished off the linear regression ideas. We skipped the KNN a little bit. We are going to be getting back to that when we continue the linear discriminant analysis. Then we're going to look at that non-parametric approach a little bit, kind of like as a competitor to this. We've talked about logistic regression, which we see that logistic regression linearizes the odds to get the logit, because that's a binary response now. So you can't treat it as an ordinary regression. You have to use a different method of analysis. Binary response, logistic regression. Linear discriminant analysis is also going to be a binary response. So this is going to be a competitor to logistic regression. And then we surveyed this MANOVA idea, which we can do some reading in that for next week, and then we return to the linear discriminant analysis. So really, when we're talking about this classification idea, we're also talking about MANOVA, but the book doesn't talk about MANOVA. That's why we're taking that slight detour into the other book. And I will post that book, and you may find the book also useful for reading on discriminant analysis and other things too. Okay, so that's it for this week, and we will see you next week.